Okay, so in the Miller-Urey's famous experiment that was done in 1951, what they did was the following. They took some gases, ammonia, methane, and several others. They were not gases chosen at random, and they were not gases chosen because there was a reason to think the earlier Earth atmosphere had these. They were chosen because they would be more likely to give the right answer, okay? If you're going to try to get a chemical reaction, what you want are some energy-rich chemicals to react. If you have molecules that aren't energy-rich, you can put them there until hell freezes over, nothing happens. And so, being a Nobel Prize-winning chemist, Urey knew that, and so they put together what I considered some very energy-rich chemicals. And then they made a little test apparatus. You've probably seen it if you've been through books of science, in which they were going to introduce these gases. They were going to have them sparked, simulating what? Lightning as a source of energy to sort of help the chemistry get going, to get the reaction started. And then to look at the reaction products. It was being circled around, and they had a little trap where they were going to catch the different reaction products, not the reactants. And then they would chemically analyze those after the experiment was over. And lo and behold, they did get these gases to react. That's not remarkable. That's as remarkable as saying, look, water runs downhill. Who would have thunk it, you know? If you put energy-rich chemicals together, if you spark them, guess what? They're going to chemically react. So there was nothing particularly special about that. But they did, in fact, when they got to looking at the reaction products, they did find, indeed, a lot of stuff that I would call organic junk. But they did find a small percentage of the molecules that were formed were building blocks that would be precursors to developing protein or DNA or RNA. So they got some successful and encouraging results out of that, though they did it with an atmosphere that was completely unrealistic. We can all be thankful that our atmosphere is not full of ammonia and methane, or we would all be dead. But if you hypothesize that, then you can do that. And so that was the first big deal. Now, what's interesting to me is at the time we're writing the book, this is like 30 years later, and they're still trumpeting this as a big, huge step forward. And the reason they're trumpeting it as a big, huge step forward is they've had no more steps, okay? Seriously, they really weren't having success on hardly any other fronts. And so you look in the textbooks, and they'll have maybe 150 pages or 100 pages on evolution, and then they'll have 2 pages on the origin of life. And then those 2 pages will mostly be about what? Ammonia and methane chemically reacting. Who would have thought it, you know? The people who got in a town close to where we lived, they had a big ammonia fertilizer plant that blew up. And it blew up about a third of the town. And it made the point very clearly that ammonia is very, very energy rich. It's very explosive. So sadly, some people got killed. But the point for us is what? Lots of energy, provide a little bit of a way to trigger that, like a lightning, and you can have chemical reactions taking place. So that was still, and it is even today in some cases, being trumpeted. I had the opportunity, after writing the book, to be on textbook review in Texas for 3 times in a row having to do with life science. And Texas is one of the few states where you actually have review. They actually recruit people from the public at large to try to give unbiased reviews. And so I was happy to do that. We worked in groups of 4, and by being in a group of 4, that was so that somebody who had a strong bias wouldn't be able to sort of recommend changing things unless there were other people that looked at it and said, yeah, that's a good idea. So I had 3 other people on the same committee that I was on as we were looking at the biology books. And we weren't looking just at the origin of life, we were looking at other things. But it was great to have the opportunity to do that and to recommend that let's at least tell the truth about that experiment. We've been trying since then to get similar results on atmospheres that are not so energy rich but are more likely to have occurred. And guess what? We've not been success. There are no great success stories. But the least they can do is to say, yes, this was an experiment. People were all excited. But it really wasn't a good simulation experiment because it was using the wrong atmosphere. It And it was an atmosphere that wasn't chosen by accident. It was chosen because we know these things will blow up, they will explode, and so there'll be plenty of energy to get these molecules to form. Roger Olson, one of my co-authors, was able to join in on this whole thing as we were writing the book and do it in a more in-depth way because of his background. He's a geochemist. You may never have met a geochemist, but it's people who do chemistry, but particularly what? On rock formations and the kind of things that geologists. So it's kind of a hybrid between being a chemist and being a geologist, which is perfect. If you're going to say, what was the atmosphere like 5 million years ago or 2 million years ago or so, how are you going to get that? You can't just go out and measure the atmosphere today. That's not going to be very helpful. But what you can do is that you can look at what I would call fingerprints in the rocks because what things look like when they're being formed, when rocks are being formed, will be influenced by what the atmosphere was at that time. And so you can infer from that with the right experiments and right knowledge, you can find out what's going on. And so Roger was able to go back and do this. Now here was the critical question. Did we have oxygen in the early Earth's atmosphere or not? And it turns out that on that question turns even additional potential problems with having a early naturalistic formation of the building blocks. We're not making proteins yet, we're just trying to make building blocks, but even to make those was very dependent on whether you had oxygen. Why? Because oxygen itself is very reactive, and you probably couldn't get the other chemicals to be available. If you have oxygen there, it would oxidize everything, and all you get is a bunch of dumb oxides, and they don't really work very good in living systems. So Roger was able to study that and to be able to verify that some of the key questions about what was the atmosphere. If you're going to run a simulation experiment, then you should really run it with the atmosphere that was there at the time. So these are the kind of things that we have been involved in the process of writing this book. I'm almost out of time, so I'm going to jump past all the really interesting stuff that you would have enjoyed. I've got to tell you one story, and I'm going to take. I think they didn't reset this when I started, so I'm going to try to do another minute or two. Can I negotiate that with somebody? I don't know. I'm not going down. Not till I get. I'll finish when I'm finished. In 1986, the International Society for the Study of the Origin of Life had their worldwide meeting in Cal Berkeley, and it was my great opportunity to be able to go to that meeting and to find out what was going on at the time around the world. They had 500 people come, and that was probably almost all the people in the world who were serious researchers in the origin of life area. I actually had 2 papers that I was allowed to present there. But what happened at the end of the conference was something I've never, ever seen anything like. Robert Shapiro, that name should sound familiar. He was what? One of the people that gave us a very generous endorsement on our book. And he's the keynote speaker to close out the conference. So 300 people are all there. We're all excited to hear what he's going to say. And he starts with saying people think that RNA, the theory at that time was RNA, it's really hard to make DNA. Maybe we could make RNA, and if you don't know the difference, don't worry about it, because I can't explain it. I'm out of time. I can't explain it. I don't have time to explain it, okay? But, so he basically said that people were assuming at this time that the RNA had been made in the laboratory under prebiotic conditions, and that was in the literature. He took a reference from 1986. No, it wasn't. Couldn't have been 86. Yeah, I guess it was 86. So he took a reference from there, and it referenced somebody in 1985, and he looked, and somebody there said, "Oh yeah, RNA has been made under prebiotic conditions," and they referenced somebody else, and they referenced somebody else, and they referenced somebody else, and it traced all the way back to 1968. All of it kind of merged back to one paper. And if you read that paper, it says, we tried to find it, but we didn't find any. So, now that's stunning, isn't it? I mean, this is like gossip. You would think scientists don't do this, but it's like it was gossip that favored a certain hopefulness about how life began, and so it had a lot of followers. But then Shapiro went on and he did something that was really amazing. He said, I'm going to spend the rest of my talk explaining to you why making RNA under prebiotic conditions is impossible. And he went through, and with a very thorough, careful, without getting into all the chemical details, it basically said there's not just one or two reasons, there's about 5 or 6 reasons why this is never going to work. And at the end, at the end of presentations, they always have questions, right? Any questions? Silence. The person who's chairing the thing, any questions? Any questions? Can you? No questions. So finally, and this is a fellow who's the head, he's the chief editor for the Origin of Life and the Evolution of the Biosphere. So he's a very important person himself. So nobody will even ask one question. 300 people, they're all the famous researchers around the world. And here's them sitting there stunned and not able to sort of even question anything that he had said. So he turns to Robert Shapiro and he says, Bob, he said, I don't disagree with anything you said, but do you have to be so pessimistic? And I'm thinking, he just gave 5 reasons why this isn't going to work, and then you say that's being pessimistic? I don't think so. Okay, now I'm really out of time. I'm going to read you 4 wonderful quotes that are more interesting than what I was going to tell you. In the meantime, boy, I had a long talk prepared. See, I've never done a 20-minute talk or 20-minute talk before. I'm going to have to practice. Okay, so this is a guy who won the Nobel Prize in Chemistry 2009. And here's what he recently was quoted as saying, it is virtually impossible to imagine how a cell's machines, which are mostly protein-based catalysts called enzymes, could have formed spontaneously as life arose from non-living matter. Explaining how life began entails a serious paradox. That's pretty strong. I like that. George Whiteside, most cited scientist in chemistry in the whole world in 2012. So that means he was writing a lot of papers, and when your papers are cited, that means other people read them and think they have something important to say. Some people write a lot of papers and nobody reads them, but okay. Here's what he had to say. I don't understand how you go from a system that's random chemicals to something that becomes, in a sense, a Darwinian set of chemical reactions that are getting more complicated spontaneously. I just don't understand how that works. And then he did a TED Talk. TED Talks have really interesting things sometimes, and they're only 12 minutes, so if you don't like it, you didn't lose much time. But in this one, he begins by, he shows he has a big bowl of chicken soup, and then he has a really cute picture of a chicken, and the chicken's looking at the chicken soup, and he says, the origin of life is like, how do you get the chicken soup to become a chicken? Isn't that a cute analogy? Yeah, that's what we're talking about, reverse engineering. Okay. Robert Shapiro. Now, Robert Shapiro is writing this in 2003. Maybe it's even later than that. It reflected his thinking all the way till he died. But much after he had reviewed our book, by about 20 years, he says, a profound difficulty exists, however, with the idea of RNA or any other replicator at the start of life. Existing replicators can serve as templates for the synthesis of additional copies of themselves, but this device cannot be used for the preparation of the very next such molecule, which must rise spontaneously from an unorganized mixture. The formation of an information-bearing homopolymer through undirected chemical synthesis appears to be very improbable. And then finally, and surprisingly, Richard Dawkins, does that name ring a bell? I don't know that he's the world's smartest atheist, but he's the world's loudest atheist. And he writes books and he goes around and talks, and he's all pretty caustic about it too, not sweet at all. Here's what he says. The universe could so easily have remained lifeless. It is an astonishing stroke of luck that we are here. That's a big concession, isn't it? Coming from him, I mean, that's a really big concession. A stroke of luck. That's a great explanation for how we got here. Okay, I am out of time. I apologize. and you'll get a shorter break to make up for it. Thank you for your time.